In the motion examples we've looked at recently, where we have had energy transfers and changes of energy from one form to another, it's typically been the case that when the system loses kinetic energy during some time period, the system could, in principle, gain all of that energy back, meaning all of the kinetic energy that was lost could later be recovered as kinetic energy. As one example, let's look at this case where we have a mass oscillating vertically on the end of a spring. We will look at this case in detail in an upcoming lab. Now, if we consider as our system as just the mass, then we know that the kinetic energy gains and losses are due to works done by the weight force and the spring force. We see the change in kinetic energy here shown in blue in the graph, and we see that sometimes these forces transfer kinetic energy out of the system and sometimes back in. Or, if we make a different choice of system that includes the agents, the spring and the earth, then we can describe the shuffling of energy around as changes in potential energies, along with the change in kinetic energy of the mass. These kinds of energy changes, which involve only at most potential energy changes and kinetic energy changes, are always reversible, regardless of what system we choose here. We see that the mass isn't losing any kinetic energy in the long run. However, this doesn't always have to be the case. There are other types of forces that we call dissipative forces, which reduce, which dissipate the energy that once was accessible as or associated with the system's kinetic energy. We've already encountered examples of these kinds of forces. Friction is one such force. We know that if we give a box a shove, the box starts out with some kinetic energy, but eventually, as the box slides across the floor, the box will come to rest. It no longer has any kinetic energy. We say that the energy was dissipated by friction. The drag force we studied earlier is another example of a dissipative force. Recall that one way we could model drag is as a force that is proportional to the magnitude of the object's speed and oppositely pointed to the direction of the object's motion. Let's say we add this force into our spring mass model here, so that there are three forces acting on the mass: the weight force, the spring force, and the drag force. By the way, our spring mass model that includes drag describes approximately what happens in a device called a shock absorber, which is used to cushion the ride in vehicles. Here's what the motion would look like for some choice of drag coefficient B. We see that while the mass starts out with some kinetic energy, after some time it comes to rest. Again, we say that the energy was dissipated, in this case by the drag force. What happened to the energy that started out as the system's kinetic energy in these cases? Let's emphasize here one place the energy did not go. The loss of kinetic energy does not show up as a gain in some potential energy because dissipative forces cause irreversible changes in kinetic energy. Such forces cannot be associated with potential energies. So, again, we ask, where did that energy that was initially present as kinetic energy go? We address this issue in our next lecture.